This is the lesson for pre-calculus for Appendix A2, where we will add, subtract, and multiply polynomials, find special products of polynomials, factor polynomials using special products, factor trinomials, factor by grouping, and evaluate using function notation and substitution. And for the first day, we'll try to get through example number 8. So, away we go. Polynomials and factoring, adding, subtracting, and multiplying polynomials. This should all be review from Algebra 2, but there are some pieces in here that might be written a little differently in the pre-calculus book. A polynomial in x is any expression that can be written in the form a sub n, x to the n, and then you'll notice that you see that the subscripts are going to go down by 1 for each one of these, and the powers go down by 1, and that's in standard form. We always have descending order for our exponents. N is a non-negative integer, so we don't have any negative powers, and a sub n is not equal to 0. A sub n minus 1, a sub 1, a sub 0 are real numbers, and those are called the coefficients, with a sub n, the one in the front, being called the leading coefficient. The degree of the polynomial is the highest power of the exponent, which in this case, when it's in standard form, will be the very first exponent that we see. A sub n is that leading coefficient that I said just a minute ago when the polynomial is in standard form. So the leading term has the highest power for the variable, which is the degree, and then the number that it's in front of that is called the leading coefficient. Standard form, a polynomial written with the powers of x in descending order. A monomial is a polynomial, not polygon, with one term. Binomial is a polynomial with two terms, and a trinomial is a polynomial with 3 terms. Now, we have to add, subtract, multiply. Eventually we'll divide, but not in this lesson. To add or subtract polynomials, you have to have like terms. Combine, add or subtract the like terms. Like terms have the same variable raised to the same power. X squareds can only be added to other x squareds. XY's can only be added to other XY's, etc. So in example 1, we have adding and subtracting polynomials. And for A, I notice that the parentheses really aren't doing anything. What they're doing is they're showing me that these are two polynomials that I need to add together. So I can really drop the parentheses. What I'm focused on is combining those like terms. So I have an x to the third here and here. Those are two like terms. 2x to the third plus x to the third is 3x to the third. Then I have some x squareds. I have a minus 3x squared plus 2x squared, which will be minus x squared. I have a plus 4x and a minus 5x, which is minus x, and then a negative 1 plus 3, which would be 2. And that's my polynomial. That's the resultant that I get right there. So 3x to the third minus x squared minus x plus 2. Now in the next one, the parentheses are doing something, because notice this one is subtraction. And one of the most common mistakes that's made in mathematics involves negatives. Anytime we see negatives, we sometimes miss them. So what I want to do is just drop the parentheses in the first set, but distribute the negative for the second set of parentheses, because I'm supposed to subtract all of those terms. And then go about combining my like terms. I see that I have a negative 2x to the third, that I have 4x squared minus x squared, which will be plus 3x squared. I have plus 3x plus another x, and that'll be plus 4x. And then I have a minus 4 and a minus 2. That would give me a negative 6. So negative 2x cubed plus 3x squared plus 4x minus 6 is that result that I get when I have those together. So adding and subtracting is just combining like terms. Like I said, a lot of review. Then these say expand the product of two binomials, and we have our two binomials, 3x plus 2, and then the quantity 4x minus 5. And it says we could use the distributive property, because we absolutely could. We could say, I'm going to take 3x times both of these terms right here. And then to finish this up, I'll take a 2 times both of these back here. That would get us the result. So that would be 12x squared minus 15x plus 8x minus 10. And then we would combine like terms, so we'd have 12x squared minus 7x minus 10. Now, that's not the way that most of you have learned it, because when you were in, it would have been an exponential. What they teach you is FOIL. And FOIL is just a fancy method, nice mnemonic device to help people remember how to multiply binomials. So with FOIL, you do first times first, which would be 12x squared. And then you do outside times outside, negative 15x, didn't write the 1 down. And then inside times inside, and last times last. And when you've made FOIL guy, here's his little eyes right there, then you know you've multiplied everything that you needed to multiply. And again, it's just a way to have a mnemonic device to remember how to multiply two binomials. You get the exact same answer. The answer doesn't change. Then, example 2 says, here's a different way of looking at this. We have multiplying polynomials in a vertical form. And we're so used to seeing all of this in a horizontal form that it's probably more natural for us at this point. But this is another way, like it says, we could write the quantity x squared minus 4x plus 3 times the quantity x squared plus 4x plus 5, a trinomial times a trinomial, in this vertical form. And then think about how you learned to do the multiplication of just basic numbers back when you were in grade school. You would take this last number, this last position, and you would multiply it times each of the terms above it. So that's what I'm going to do. I'm going to take 5 times 3 and get 15, 5 times negative 4x, and get minus 20x, 5 times x squared, and get 5x squared. Now I'm done with the 5, taking care of that. And I move to the left and I see I have a 4x. So now I start again with 4x times 3, but I'm going to line that up under the other x term, under the like term that I have with that. 4x times a negative 4x would be minus 16x squared. 4x times x squared would be 4x to the third. So lining those up vertically. Now I'm done with that 4x on the bottom, and I'm up to the x squared. And I take x squared times each of the terms, starting up there with the 3. So that would give me 3x squared minus 4x to the third and plus x to the fourth. Again, lining those up so that I can combine like terms. And what I have is x to the fourth. I don't have any more like terms for that. But 4x to the third minus 4x to the third is going to be 0. And then I have 5, 8 minus 16, negative 8x squareds. Negative 20x plus 12x would be minus 8x plus 15. So we get the result there. And it's just kind of a different way to organize your math. So x to the fourth minus 8x squared minus 8x plus 15. So the steps are over here. Multiplying polynomials in vertical form, we have arrange polynomials in standard form, one on top of another, align the terms vertically, and then multiply each term of one polynomial by every term of the other, and finally combine like terms. Now, moving on, special products, things that we should notice when we're trying to multiply binomials together. And you're going to see here that the upper powers ask you to remember a little bit about Pascal's triangle. So special binomial products, let U and V be real numbers, variables, or algebraic expressions. And we have the product of sum and difference. So when we see that we have two binomials and they have the same first and last term, but one has a plus addition in there, and the other one has subtraction, then we should notice, hey, that should go really fast because outside times outside and inside times inside would cancel each other out when we do FOIL. And that gives us u squared minus v squared. The square of a sum is the quantity u plus v squared, and we start to see a formula, u squared plus 2uv plus v squared, which I'll be showing you how we could figure out what those numbers should be like when we look at Pascal's triangle. And then for the square of a difference, you'll notice that the only change is going to be that the second term is now negative, and that's because outside times outside plus inside times inside would be two negative terms. Then we have cube of a sum. So this would really be the quantity u plus v times the quantity u plus v times the quantity u plus v, which of course we could do. You know, it would take us a while to get it all there, but we could write that out the long way and find it. And the same thing with cube of a difference. But these formulas are supposed to give us a way to do this a little bit faster. And as I said before, they come from Pascal's triangle. So Pascal's triangle starts with ones in a triangular pattern up at the top. And then to get the next rows, you always start with a 1, but what you do is you add the two terms that are above it and end with a 1. So this would be 1, 2, and 1, and then the next one would be 1, 3, 3, 1. And it turns out that Pascal, he was very intelligent, and he actually had a lot to do with, there's a language in computers that's called Pascal's language, and he started talking about row 0, and then row 1, row 2, and row 3. And it was discovered that those numbers that we see in Pascal's triangle have all kinds of applications in mathematics. Some of them include probability. What we're seeing here is that these are the coefficients for our special binomial products here. Because if you take a look at this first one, u plus v squared, the first special product that we have that would fall under Pascal's triangle, we have a 1, a 2, and a 1. A 1, a 2, and a 1. And then we go down to cubed, which would be row 3 of his triangle, and we see 1, 3, 3, 1, 1, 3, 3, 1. So Pascal's triangle helps us when we get to binomials where we're, well, cubing, raising it to the 4th power, raising it to the 5th power, etc. Have a way to do that so that it's supposed to make it easier and faster, definitely faster. So when we're using special products, this first one says expand the products. You do want to stop. You don't want to automatically do FOIL. You want to stop and analyze and say, oh, this one has a plus and this one has a minus. I don't need to bother with outside times outside and inside times inside. I'll do first times first and last times last and get 9x squared minus 64. P for B, 5y minus 4 squared. Well, now we have two ways to do that, because we certainly could, and most people will. We're really fast at FOIL, so one of the things we do is tend to overuse it a little bit, is just write them out twice, because the powers, they always affect what's to the closest to them on the left. And in this case, that's parentheses. So that means we need to write the parentheses twice. And then, like I said, most people would just use FOIL, realizing that this is special because your two outside times outside and inside times inside terms are going to be exactly the same. So you've got negative 20y twice, which will be negative 40y plus 16. So you won't find a lot of people that use the special patterns for figuring out, binomial squared. But when we get to C, definitely it is a time saver to use the formula. So I look at this and I see this is the quantity, and your book used u minus v cubed. And I remember Pascal's triangle, and that third row was 1, 3, 3, 1. But I'm going to start this a little differently. I want to think about the patterns that are involved. And I realize when I go back up here that I see the u was to the 3rd power, then the 2nd power, then the 1st power, and there it wasn't there at all. And that was because it was u to the 0. So the first term starts off with the highest power, which would be u cubed, then u squared, and I'm running out of space here, so I'm going to put it down here, u to the 1st, and then no u. And then the last term, which in this case was v, starts off with the lowest power, v to the 0, v to the first, v to the second, v to the third. And so I will put v to the first, v to the second, v to the third. And then, like I said, I start thinking about Pascal's triangle. And those numbers for row 3, which were 1, 3, 3, 1. And last but not least, I need to know what's going on with the signs. Well, when you look at the signs in the quantity u plus v squared, you see that those are going to all be pluses, which makes sense because it would be the quantity u plus v times the quantity u plus v times the quantity u plus v. But in u minus v, we have to notice that it starts positive, then goes negative, positive, and negative. So it oscillates between positive and negative, and it always works that way. So the first term is always positive, and then the second is negative, the third is positive, and the last is negative. Again, no matter what power we raise that to, that first term will be positive, and then you oscillate with a negative, positive, negative, positive. So with this one, what I want to do is realize that my u is 2x, and my v is 3y. I don't need to worry about the signs. The signs are taken care of with the formula. So this will be 2x, the quantity cubed, and then I go to the next position, and I see, I'll put the 1 out there, I don't want anybody to lose that, minus 3, and then I need 2x, the quantity squared, and I need a 3y, because that's v to the first. All right, so next term up here with that pattern, plus 3 times 2x to the first power, and then times 3y squared, and finally minus 1 times my v, which was 3y cubed. So now I just have it, in an organized fashion, and I can think about the fact that I have to use the order of operations to get this thing done. So first term right here, I need to take the 2x, the entire quantity, to the third power. So 2x times 2x will be 8x to the third, times 1 is of course just 8x cubed. Now in the next one, I want to think about those powers first. This 2 squared will actually be a 4. So this would give me 3 times 4, which is 12, times 3, which is 36. So minus 36. And then I would have an x squared and a y. So it's really important that we remember order of operations. We have to do the exponents first. Then the next term, we'd have a 3 and a 2, but again, this power has to be done before I use that 3 and a 2, and that's a 9. So 3 times 2 is 6, and 6 times 9 is 54. So plus 54, xy squared. And then I have my very last term back here, which again, the powers would come first. So we'd have 3y times 3y times 3y, which is 27y cubed, and then we'd have that negative 1 out in front. So there it is. And like I said, this becomes a big time saver when you are raising binomials to the third power or higher. And it's just formula that we need to get used to. And we need to get used to Pascal's triangle and how to use that. Now, factoring polynomials using special products. So this is the reverse. We've seen how to multiply them. Now we're going to factor. Factoring the polynomial is writing a polynomial as the product of 2 or more polynomial factors. In this appendix, factor polynomials to a lesser degree with integer coefficients. So we're never going to be trying to factor a half times 3/4 or anything like that. We're just going to use the integers. Integers are the numbers like -3, -2, -1, 0, 1, 2, 3, and on forever in both the positive and the negative direction. A prime polynomial is a polynomial that cannot be factored using integer coefficients. So if there isn't anything that we could factor this into, then it's called a prime polynomial. A polynomial is completely factored if it is written as a product of its prime factors. So we see here we've got the steps for factoring polynomials. And these steps, we always follow this rule when we go through. One is factor common factors from each term using the distributive property. That would be what you've heard before called factoring out the greatest common factor. So we look at it and see, is there something we could take out of all of this? That's a must. It's going to make the problem much easier. Number 2 is recognize the expanded form of the 5 special binomial products. So is it special? Something there that we see that just grabs us. 3 is use factor pairs if it is not one of the 5 special binomial products. And that's going to be our key is, hey, can we just go back to old-fashioned factoring and find something that would work here? And then 4, I guess I kind of include in number 2. If there are 4 terms, try grouping, because that is a special product that we see. We'll notice because it has 4 terms, and we'll look at it and say, well, this isn't a trinomial. How do I factor this? And with 4 terms, we should try grouping. So for example 4, we just start with removing the common factors. And so I'm taking a look at A, and I'm thinking, well, they're all even. I can take a 2 out of them. Oh, look, they all have an x. So I could take a greatest common factor of 2x out, and then kind of think backwards. 2x times something gives you 2x squared, 2x to the third, and that something is x squared. And then 2x times x would give you 2x squared, and times a negative 3 would give us what we need. And then you have to think, all right, is that factorable? Can I keep going? Because whenever we have a squared term, we should always think, can I do something here that'll make this work? So x squared plus x minus 3, there's nothing special about that. That is not a perfect square binomial. If it were, the first and the last terms would be perfect squares, and negative 3 is not a perfect square. So I start thinking, are there 2 numbers that multiply to negative 3 and add to 1? Well, you have negative 3 and positive 1, but that adds to negative 2. And then we have positive 3 and negative 1, but that adds to positive 2. So this one's done. That was the best we could do, was just to pull out the 2x, which is factoring out the greatest common monomial term. For B, I notice they both have u's and v's. So I'm going to take one u because this one only has 1, and one v because the other one only has 1 v, and then think backwards about, well, how would I get that if I were to multiply? Well, I'd need a couple of more u's, but that's all I would need for that first term. And then in the back, I'd need a couple of more v's. So there's my v squared. Now, I still have squared terms, so the question is, can I keep going? Can I keep factoring? And we can't, because this is the sum of 2 squares. There's no such factoring pattern for that, for u squared plus v squared. If it were u squared minus v squared, that would be different. That's the difference of 2 squares. But this one, we're not going to be able to find terms that would give us a u squared in the front and a v squared in the back and add to 0 in the middle. It isn't going to happen. Now, here's where we say, you know what, we already took out the greatest common monomial terms. Now what do we do? But that's our first step, always. Can we pull something out of both of these? So example 5 says factoring the difference of 2 squares, which I'm not always going to get that header when I have to go ahead and factor. So I look at 25x squared minus 36, and I think, boy, could I pull something out of both of those? Is there a greatest common factor? And the answer is no, but while I'm looking, I notice this is 5x squared, and this is 6 squared. Well, then I don't want to factor out a greatest common monomial term because this is going to work out great. I don't have a middle term. That means that outside times outside plus inside times inside, those 2 terms have to be opposites to add to 0. So this will be a 5x and a 5x to multiply to give us 25x squared. And then we'll have to have a plus 6 and a minus 6 in the back in order to make this work. And there are no more squared terms, so there would be nothing else that we can do there. Now for B, this one's a little bit different. So this is where we take what you've learned in Algebra 2 and then we step it up a little bit. And we say, all right, let's see. There's not a greatest common monomial term, but that's 2x squared, and this is y plus 3 squared. Oh, this is a difference of 2 squares. We see the opposite sign. We've got the negative right here. And realize, okay, so what do I need to do? I need a 2x in the front for both of these. And I better make this a little larger. I'm not going to have any room to write. I need a 2x because 2x times 2x will give me the 4x squared. And in the back, I need a y plus 3 in both of these. But one has to be a plus and one has to be a minus. And in my first set of parentheses, I realized, boy, I got a lot of parentheses going on there. I'm just going to drop those because they're not doing anything. But in the second set, my parentheses are doing something because I have that negative sign in front of them. So I want to distribute that so that I can see what this would look like. So there it is. We actually end up with two trinomials that would work for this one. The quantity 2x plus y plus 3, and then the quantity 2x minus y minus 3. So that's a little interesting use there of our difference of two squares methods. Now, as we move on, we want to look for those that are maybe a little bit tougher to spot, but it's always look for the greatest common monomial factor first, then look for these special patterns. And this one is a perfect square trinomial, and it's the square of a binomial, and it has one of the two forms shown below. And you're going to notice the only difference is that one is all addition and the other one has subtraction between the first and second term. So here's what we're looking for if we're going to factor. We're going to notice that this is u squared, and then the last term is v squared. So those are perfect squares. In order for this to work, when we multiply u times v and double it, we have to get the middle term. Otherwise, it's not a perfect square trinomial. It also works back here when we have subtraction. This is u squared and this is v squared. And when we multiply those together and double it, we need to get the middle term. So don't think about whether or not it's positive or negative, just check that middle out. Because to take care of whether or not it's positive or negative for the middle term, we're just going to change the sign between those two factors. So example 6 says factoring perfect square trinomials, and yeah, they kind of gave away the punchline here. So I'm looking at A and I'm thinking, is there anything I can factor out of all three of these? And no, there's not, because 9, 6, and 1. 1 is the only thing we could pull out, which isn't going to help us. But I notice while I'm checking that the first term is 3x squared, and the last term is 1 squared. So I start to think this might be a perfect square trinomial. 3x times 1 times 2, oh yeah, 3x times 2, that's going to be 6x. So I can write this as one binomial squared. And I already know what has to go in the front and the back. That's the 3x and the 1. All I have to do to figure out whether or not it's plus or minus is to look right here between those first two terms. So this would be a plus. For B, again, I start thinking greatest common monomial factor, 4, 12, and 9. Oh, rats, I can't take anything out, but wait a second. This is 2x squared, and this is 3y squared. Maybe if I multiply those together and double it, I'll find this is a perfect square trinomial. 2x times 3y is 6xy, and when you double it, you do get 12xy. So we already know what goes in the front, and we know what goes in the back, and that it's going to be squared. And then we just take a look between the first and second terms, and we see subtraction, and there we go. It's done. So you want to check for those special patterns after you've checked for a greatest common monomial factor. Now this one says in the sum and difference of two cubes, notice the pattern of the signs. Well, you should notice there's a pattern with all of this. The first thing that I think is I don't memorize. As a math teacher, I just think that's dangerous to learn to memorize things, because if you don't use it, you lose it. So I try to think, how could I figure this out myself? Using logic, u cubed plus v cubed. Well, if there's 3 of them, u cubed plus v cubed, there's got to be at least one that would factor out of there. So there's my logical thinking. And then I think, all right, if I had u plus v, how would I get back to u cubed plus v cubed? Pretty obviously, I would have to take u times u squared to get u cubed. And I would have to take v times v squared to get v cubed. But what I don't want to happen when I multiply this back together is that I get a middle term. So how do I get rid of the middle term? By the fact that this is a plus and this is a minus. Those will have opposite signs, and so my middle terms will drop out. So that's how we think through these formulas. Same thing with the one that has subtraction. If it's u cubed minus v cubed, seems pretty logical to me. There ought to be at least one u minus v we should be able to pull out of there. And u times u squared would give me u to the third. V times v squared would give me v to the third. But then my middle term has to have the opposite sign in order to make sure that when I multiply this together, I don't get a middle term because it has to result in u cubed minus v cubed. So looking at example 7, I do think, hey, let's factor out a greatest common monomial factor, but that thought is gone in less than a split second because I see that I have a perfect cube. We have x cubed and 4 cubed. So I think about my formula, which would be the u cubed minus v cubed, and the fact that u minus v would be an obvious choice for something that could factor out of that. And then I think I would need a u squared in front and a v squared in the back so that I could get back to u cubed minus v cubed. But that's probably going to give me a middle term when I do that. So what I have to do is figure out how to get an opposite middle term in this one. And that would be plus uv, and that's because this one already had a minus in it. So now what I do is I just substitute in x for u and 4 for v. So this will be the quantity x minus 4 times the quantity x squared plus 4x plus 16. Now the question is, are we done at this point? And we would want to know, should we keep trying to factor x squared plus 4x plus 16? Most of the time, when you have this either sum of two cubes or difference of two cubes, you're done. However, that doesn't cover it because we need to know we're finished. So x squared plus 4x plus 16, I want to know whether or not that's going to be factorable or not. And one of the things that you can do before you spend a whole lot of time trying to factor something that's not factorable is use the discriminant, b squared minus 4ac. If the discriminant comes out to be a perfect square, well then you know that it is factorable and you need to keep going. So we've got ax squared plus bx plus c, and in this particular problem that would give us 4 squared minus 4 times 1 times 16, and that's going to be 16 minus 64, which I know is negative, and you can't have a perfect square that's negative. So I know I'm done. And like I said, 95 to 98% of the time with these difference in sum of two cubes, you are finished when you get to that point. I take a look at B, and I think, okay, can I pull out a greatest common monomial factor? I can't. But I saw something good. 2x cubed is 8x cubed, 2x the quantity cubed, and then 3 cubed would give me 27. So this is a sum of two cubes. And again, I think about my formula. My formula would be u plus v this time, so that would be 2x plus 3. And then I would have to remember to do 2x the quantity squared, which would be 4x squared. And in the back, I would need a 9 to make sure that 3 times 9 gives me 27. And in the middle, because this was addition, I'm going to need subtraction of that u times v term to make that disappear. And again, if I'm worried, especially with this one, you take a look at it and you think, well, this might be another perfect square. It might be a perfect square trinomial. This is 2x squared. This is 3 squared. That's 6x. If I double it, oops, I don't get negative 6x in the middle. Gosh, I wonder if I'm done. So b squared minus 4ac would be negative 6 squared minus 4 times 9. And you realize again that that would come out to a negative discriminant. So we are done. That was as far as we could possibly go. Then, factoring trinomials. We have checked for a greatest common monomial factor. We checked for special patterns, and they're not there. And we still have to figure out, how do we factor this? Well, it says factoring the trinomial ax squared plus bx plus c into the product of binomials with integer coefficients requires factoring the integers a and c. So what we do is we find all the numbers, all the nice integers that would multiply to give us a, and all the nice integers that would multiply to give us c. And then, because we know outside times outside has to be added to inside times inside, we check to see, do we know of any that would add to b in the middle? So example 8 says factoring a trinomial with a leading coefficient of 1, which is actually huge because it makes the problem easier. And I check for a greatest common monomial factor. and it's not there. I check for a perfect square trinomial, but negative 14 is not a perfect square. So now I try good old-fashioned factoring, realizing that x times x will give me x squared. And I just look for two numbers that multiply to negative 14 and add to 5. And I realize, well, if I use 7 and negative 2, 7 plus negative 2, that's 5. So positive 7 and negative 2. And there are no more squared terms, so we're done. We have that into its linear factors. For B, we want to factor this one. Again, I try greatest common monomial factor. There's nothing I can do. Then I look and see, oh, could it be a perfect square trinomial because there's y squared in front? Nope, 30 in the back is not a perfect square. So I try good old-fashioned factoring, where I have y times y for y squared, and I'm in need of two numbers this time that multiply to 30, positive 30, but somehow add to a negative 11. So I realize that's going to have to be two negatives, and that would be negative 5 and negative 6 that would make that happen. So that is the first day. Obviously, we couldn't get through everything for the A2 section, so we'll be finishing that up. But what we want you to do is go through this assignment doing as many of these as you can as you get to it and you think, oh yeah, we talked about that. That's a perfect square trinomial. Oh, we talked about that. That's a sum and difference of two cubes. But if you get to anything that you're saying, we haven't done that yet, the number in front of all of this won't factor out, and we haven't talked about factoring when a is not equal to 1. We haven't factored by grouping yet. Just hold off. Don't do those. Wait until we hear the explanation, because the danger is always that when you do something that you think you remember, that you might do it wrong, and then place it in your long-term memory as an incorrect memory. So please do what you can on those.